China is about to send a hopper into the dark, away from the only light that keeps it alive. That is the mission at the edge of Shackleton crater. On one side, a rim near the lunar South Pole, where sunlight can keep machines awake. On the other, the black floor of a crater that may not have seen the sun for billions of years. One of the coldest places in the solar system. The thumbnail says into the dark because that is exactly where the prize is. Everything keeping Chang'e 7 alive stays behind in the light. The water it came for is ahead in the dark. That is the trap. The mission begins with that divide. The lunar South Pole matters because it may hold water ice locked inside permanently shadowed regions. These are craters where the sun never climbs high enough to reach the floor. At the poles, sunlight comes in low, almost sideways. Raised rims can stay lit for long periods. Deep interiors can stay black for ages. That geometry creates the whole mission. Water ice cannot survive easily on the sunlit moon. The surface heats, freezes, and gets blasted by radiation. But in permanent shadow, the cold can preserve volatiles that would vanish almost anywhere else. That makes those craters some of the most valuable places on the moon. It also makes them some of the most hostile. A spacecraft survives by power. Power needs sunlight, unless the mission brings another source. In the dark, solar panels stop helping, batteries start counting down. Electronics face extreme cold. Mechanisms stiffen. Thermal margins shrink. The same shadow that may preserve water can kill the machine sent to find it. The thing China came to measure is in the one place the mission cannot simply stay, and every hour outside the light reduces margin. Chang'e 7 is built around that contradiction. The launch is targeted for the second half of 2026, with reports pointing to August, but no fixed date has been publicly locked. The important part is the design. It is not one spacecraft, it is a stack. An orbiter, a lander, a rover, and a hopper, with KCAO-2 relaying communications. Across them are 18 science payloads, some built with international partners, but the architecture only makes sense when seen through one resource: light. The lander targets an illuminated rim near Shackleton crater, close to the lunar South Pole, around 123.4 degrees east and 88.8 degrees south. That rim is not just a scenic landing site, it is survival infrastructure. Sunlight means power. Sunlight means heat. Sunlight means time. The lander never has to leave the sun. The hopper does. The rover also lives by the same rule. It is based on China's earlier U-2 rovers, but at the South Pole the problem is harsher. The sun stays low on the horizon, shadows stretch across the ground. A route is not only a path across terrain, it is a path through changing light. The rover has to plan where it drives and when it sleeps. It has to use local illumination to keep itself alive. Its movements are tied to the low polar sun. Too long in darkness, and the mission starts losing energy instead of gaining science. Across this whole mission, the light decides what survives. That is why the hopper matters. It is the one part designed to break the rule. A mini flying probe with legs. Not the rover, not the lander. A small machine built to leave the safe side of the mission and jump into the shadowed terrain where the water may be waiting. The hopper is expected to fly at least 10 kilometers per hop. Its target is not the sunlit rim. Its target is the dark interior. It has to descend into a shadowed crater, land on terrain the sun cannot rescue, and do science before the cold and power limits close in. The coldest place in the solar system, and China is going to drill it. Landing is only the first disturbance. Rocket exhaust, dust, and contact with the surface can contaminate or alter the exact spot beneath, so the hopper has legs. After touching down, it moves away from the area disturbed by its own landing. Only then does it begin the part that matters. It drills. The instrument is the Lunar Soil Water Molecule Analyzer. It takes regolith from the shadowed ground, heats it, and drives off trapped gases. A mass spectrometer then sorts what comes out, separating water from methane and other volatiles. The goal is not to infer water from orbit, it is to measure it on the ground. That is the moment the whole mission is built around. But it cannot end there. The hopper is not being sent into the dark to stay there. It has to fly back out, back to sunlight, back to the one environment that lets it keep operating. Into the dark, drill, and back to the light on its own power in the cold. It is not a trip into the dark, it is a trip back out. That return is the hidden risk. A descent can succeed and still leave the machine trapped. A drill can work and still burn time the hopper cannot spare. A sample can be taken, heated, and analyzed, but the mission still depends on leaving the shadow before the environment takes over. Land in the light, drill in the dark, and get back before the cold wins. If you want to understand the systems that these missions actually depend on, not just the launches, subscribe to SpaceWatch. The stakes are simple because the geometry is simple. Survival is in the light. The water is in the dark. Between them is the most exposed machine on Chang'e 7. The lander can stay on the rim. The rover can follow light and plan its hibernation. The orbiter can map from above. Kiao-2 can relay communications. But the hopper has to cross the boundary. It has to leave the part of the moon where spacecraft can recharge and enter the part where the thing humans want may have been frozen for billions of years. No public source gives a clean answer to the question that matters most. How long can it last down there? How much power does the round trip leave behind? How much cold can the instrument tolerate before the margins disappear? The mission is not only asking whether water is there, it is asking whether a machine can survive the act of going to the only place where the answer can be found. If it works, China could make one of the first direct in situ measurements of water ice at the lunar South Pole. An orbital signal would become something touched, heated, sorted, and measured. The hopper could also become the first-legged machine to move across another world, and one of the few craft after NASA's ingenuity to make separate flights beyond Earth. If it does not work, the result is quieter. The lander may still stand in the light. The rover may still drive. The orbiter may still map. But the question at the center of the mission stays in the dark. Water ice remains a signal from above, not proof from the ground. The answer stays frozen where it has been, beyond the reach of the machines built to survive sunlight. That is what makes Chang'e 7 different. Its most important measurement depends on leaving safety behind and returning before the environment ends the attempt. The mission is not just hunting water, it is testing whether the moon's darkest places can be visited without losing the machine that enters them. A lit rim, a black crater, one hopper between them. If the only way to reach the moon's water is to leave the one place that keeps your spacecraft alive, how much of the mission do you risk on the part that goes into the dark?